Okay, let's begin.
I think it fell on the floor.
Thank
Okay, so we are going to finish 1.6 and move on. I would like to backtrack a little bit because last time I think we were rushing a little bit. I don't want to make sure we didn't skip over anything that's important. So 1.6 continued. So we're learning about more on functions, in particular about their zeros and how this can help us. So recall, I'll briefly go over symmetry here. So recall the zeros of a function. Or to talk about the roots of a function, the roots of x. This just means the set of all x values, set of x values, so that f of x equals 0. So now we did some examples last time. We're actually to find the zeros of some functions. X cubed minus 4x 3. We looked at x to the 4th minus x squared 4. We looked at x cubed plus x squared minus 9x. And so now to find the zeros, all you have to do was set them equal to 0 and solve for the x value. That's basically what we have to do. So let's quickly go over these. The first one, we did this last time, but let's just quickly run through it again. Set that equal to 0. And of course, remember the standard strategy for nonlinear equations is to bring everything to one side, factor the left side, set each factor equal to 0. And so that's what we're going to do here. This guy would factor, I believe, so that's 2x and x, and maybe a 2 and a 1. This would give me a minus 4 plus 1 would give me a minus 3. X is equal to minus 1/2, and x is equal to 2. And these are called the zeros of that function. Now, one thing I also want to emphasize is graphically what this means, graphically what the zeros are. You should note the zeros, if they exist, are the same, graphically speaking, as the x-intercepts. So now we actually looked at graphing quadratics before, and you understand why it's important for us to be able to find x-intercepts. So for this one, we will know what the graph of this function can look like by looking at its zeros. So I know it will pass through minus 1/2, and it will pass through 2. So it would look like something like that, if I were to graph it. It's a positive x-coordinate and a positive coefficient for the x squared term, so I know it's opening upwards. And so not only is the zeros important they're important for many other reasons. But one thing they can do is they can help us actually graph something, because they tell us when our function hits here and hits here. Right? Now we know about how to graph parabolas. We looked at this last time. But when it comes to other things, the zeros can help us as well. Because even if you don't know the standard shapes for these guys, you can figure out how to graph them using the zeros. So again, we did this last time. You should know how to sketch a quadratic. So let's actually move on to the second one. And I want to do some naive sketches here as well, using the zeros, so you can see how I would actually go about sketching something. So if we look at 2, x cubed minus 4x. Find the zero set it equal to 0. I'm going to want to factor, so I factor out an x. I can factor further. So here I get x equals 0, x equals 2, x equals minus 2. Now, those zeros, remember, they are the x-intercepts. So one thing I want you to get used to doing is to be able to figure out graphically what things might look like, because sometimes knowing the picture of something can help you a lot in solving a problem. So what would this guy actually look like? First thing you can do is you can go in and you can plot these intercepts. 0, minus 2, and 2. Now, so we know the graph of this thing is going to hit those 3 points because those are the zeros of the function. Well, what is the function doing otherwise? Well, for polynomials, they are very nice to graph. They kind of flow continuously all the time. And so you can figure out how to graph these guys by just figuring out what position is the graph supposed to be in between each of these zeros. So one way you can think of zeros is they will break up the xy plane into sections. Right, so you can imagine that these zeros are cutting things into sections. And we can figure out the graph of something by figuring out what it's doing in each of these sections. So there is now the section that's to the left of minus 2, the section that's in between minus 2 and 0, the section that's in between 0 and 2, and the section that's to the right of 2. Right? And what you can do here is now, if you want to actually figure out what the graph is doing, you can actually plug in numbers. So for example, if I were to plug in a minus 3 into this function, right? And it's normally nicest to plug it into the factored form. It'll usually be easier, especially if you're not using a calculator and you want to see the values. Clearly, if I plug in a minus 3, this will be negative. This will be negative. This will be negative. Right? So I know the graph is negative. It's underneath the x-axis, right? So negative means below x-axis. Right? Because the y values, the output values, are negative when you're underneath here. So I know the graph should be down here somewhere. Now I don't have to know specifically where. The next calculus class is going to go into great detail into graphing things, but I want you to have some naive idea of how to sketch something. Then I could plug in a number in the other one. In the other region, like a minus 1. This will be negative. This will be negative. This will be positive. So now you realize that that gives you a positive number, so you know your graph should be up here somewhere. Plug in a number over here in this region, and the zeros really separates the regions because, and so that I only need to test one value, so I'm just testing the easiest value, because every value in that region will behave the same. So if I plug in a 1, that will be a positive here, times a negative, times a positive. So that's a negative, so I know the graph is now down here again. If I plug in a number over here, like a 3, and I'm plugging in easy numbers, or I'm not going to plug in like a 17, because, you know. So that would be positive, that would be positive, and that would be positive. So I have 3 positives. So I know the graph should be up here. So now if I wanted to sketch what this thing would look like, my graph should be down underneath in this location, in this region. It should be above in this region, it should be below in this region, and it should be above in that region. And I know it needs to hit these 3 points. So if I were to sketch this, it would look kind of like that. That's the way you can figure out what that graph would actually look like. And as you can see, the zeros were a big part in that, because the zeros tell you where it hits the axes. This breaks up your xy plane into sections. Testing a number in each section can tell you should you be above or below. And you only need to test one number, because if in this region the graph were to change its behavior, it would create another zero. So the zeros are really the only guys that you really need to worry about when it comes to this sort of thing. So you'd be able to sketch a curve just by knowing about its zeros, essentially. Finding the zeros tells you where it hits the x-axis, and you can kind of plug in numbers and check should they be a positive output or a negative output. And you don't even need to know the values, you just need to know the signs, right? So in the factored form, you just know if something will be positive or negative based on how large the x value is. And then that can help you figure out the graph. So that is a very convenient thing to know a lot of the time. So if we can look at the other one in this slide. So the calculations for finding the zeros we did last time. But now I actually want you to think in terms of pictures more. So let's look at what this one would look like. First, we'd set it equal to 0. We can factor out an x squared. We left x squared minus 1. So we can factor that further. So we got x equals 0, x equals 1, x equals minus 1. And after this, I'm going to emphasize some things to you that people tell you that you have to remember, but you don't really have to remember if you know what I just showed you. So if I were to start graphing this one, I plot here 0, so it's definitely going to touch that. It will touch here at 1. It will touch here minus 1 and 1 respectively. So again, I'm thinking of 4 sections. Now, the better you get at this, the less stuff you'd have to draw on your thing to figure it out. So I can imagine that I'm thinking in sections. And so now I'm going to plug in numbers like a minus 2. I can plug in a minus a half. I can plug in a half. I can plug in 2. Now I'm plugging them into this version. Now notice that this square here is always positive. In the intervals. So we can ignore. The less work you have to do, the better, right? That's always going to give you a positive number, so I can essentially just ignore it and worry about what these two are doing. So plug in a minus 2 here, I get a negative. Plug in a minus 2 here, I get a negative. So I know my graph should be up here. If I plug in a minus a half, I get a negative. Plug in a minus a half, I get a positive. So my graph should be down here. If I plug in a positive a half, I get a negative. Plug in a positive a half, I would get a positive. So my graph should still be down here. If I plug in a 2, I get a positive. Plug in a 2 again, I would get a positive number. So my graph should be up here. And so now I can figure out how to sketch that. So now my graph should be up here, but it needs to come down to hit this point. Then it needs to go down here, but then it needs to turn around and come back up to hit this point. Then it stays underneath because it needs to be down here, but then it has to rise up to hit that point, and then it has to go up there. So I know the graph here would look like this. So that one's a W. Now, a lot of people will tell you, well, you should look at the factors of this guy. And because this is an x squared, the guy that gave you 0 behaves like an x squared, so you have to know that this should be behaving like a parabola here, and blah, blah, blah. You don't need to know all that stuff. Find the zeros, plug in numbers, know where your graphs are. I didn't even have to mention that this was supposed to look like a parabola to figure out it had to look like a parabola at 0. So there are things that you don't even have to know when you're using this method. So it's a very good method to look at, and a lot of times it can tell you about the behaviors of functions. So another thing you'll hear about all the time is end behavior, which again, if you're doing this, you wouldn't care, right? So there's the notion of end behavior. essentially, it is what it sounds like, what the ends are doing. And you kind of have this idea, well, x to the n, both sides will go up if n is even. Whereas for x to the n, the right side would go up and the left side would go down if n is odd. And of course, if you find the negative versions of those, both sides will go down if n is even. And for x to the n, if odd, you know you would expect it to look like this if n is odd. Now, I want you to notice here, the highest power here was x to the fourth. That is clearly even. So, knowing my n behavior, the n's were supposed to go up, but it turns out, look at that. I already knew they were going to go up just by how I set up the problem. So, n behavior is another thing that people tell you to memorize all the time, which technically you don't need to if you know how to do stuff. I mean, if you know it, it's nice. You can use it as a double check to yourself. But in general, you don't even need to know it to graph something. So I could have figured out that the ends have to be pointing up like that by just plugging in numbers in between the zeros. And you'll notice here the highest power is odd. So you can know that the right side should be going up and the left side should be going down by this picture. But again, I didn't even know that when I was doing this the first time. Right? So in that way, zeros are very convenient. They not only can tell you things about the function itself, algebraically and analytically speaking, but the geometry, the zeros help figuring out the geometry. And a lot of times knowing about what's happening geometrically can help you solve a problem. Because you have an intuitive idea when a function is increasing or when it's decreasing or when it's moving up. So you know, so you can be able to talk about the behavior of the function in a much more fluid way, knowing the zeros and knowing the graphs. And the zeros can help you a lot with the graphs. Let's do the last example. So this one was an x cubed plus x squared minus 9x minus 9 equals 0. And we wanted to find the zeros of that, so we set that equal to 0. And so we can factor. There are 4 terms here, so we do factor by grouping. And remember, we're thinking of this. Remember the list of things I told you how to factor things. You should always have that in your mind. So I realize it's not 2 or 3 terms, so I skip all the way down to like step 4 or whatever of that process. Factor by grouping is what I'm thinking about. So I think of them in pairs and factor out the GCF. I should have the same thing left over, so now I can factor that out. This can factor further. That's the difference of squares, which is the last step in the factoring strategy. Always check if after things are factored, you can factor further. So here we would have the zeros are minus 1, 3, and minus 2. Now that we did last week. Now, someone help me actually do the graph here. Volunteer and tell me how to do the graph. So what would you do first? What? Plot the x's? Yeah, so if we're looking at, let's call this naive sketching. Right, to kind of summarize here. 1, plot the zeros. X-intercepts. That's the first thing you would do. So in this case, we have a minus 3, a minus 1, and a 3. What's the next thing you do? Right. Pick points in between these test them in the original, in the factored formula. You're looking for the signs. So that's the second thing. So I would pick some numbers here. Easy numbers. If you have a calculator, it's fine, you can pick whatever you want, but if you're doing this by hand, I pick stuff easy. So I can literally pick any number in between -1 and 3. I can pick 1, I can pick 2, I can pick a half, but 0 is pretty easy to work with. Right, and you test them in, you can test them in the original, but I think, especially if you're working in your head and you don't have a calculator, that's going to be harder to calculate. So to be cubing, squaring, multiplying by -9, and adding -9 is going to be harder than multiplying 3 things where you know the signs. So clearly plugging in -4 here gives me a negative. Plugging in -4 here gives me a negative. Plugging in -4 here gives me a negative. So now I know it's negative. Plugging in a -2 here gives me a negative. Plugging in a -2 here gives me a negative. Plugging in a -2 here gives me a positive. So the graph should be up here. Plugging in a 0 here gives me a positive number. Plugging in a 0 here gives me a negative number. Plugging in a 0 here gives me a positive number. That's negative. The graph should be down here. Plugging in a 4 here gives me a positive number. Plugging in a 4 here gives me a positive number. Plugging in a 4 here gives me a positive. Positive times positive is positive, so the graph should be up here. So that tells us that positive sign means graph above x-axis. Negative sign means graph below x-axis. And of course for step 4, now you just sketch. For polynomials, you kind of don't have to, and pretty much anything you sketch in this class actually. Polynomials, it will be a curvy continuous. Continuous as in non-breaking. Curve is the best word I can use there. It's a technical term. It's just something that continues, right? As long as it's not a straight line, it's going to be curving at some point, at some way. And so you just have an unbroken curve passing through those points, hitting these regions. So I know I should be at the bottom, I should be up here. Overshot it a little bit there, because I need to hit this one. So I should turn here. Now, another thing I mentioned to you is the idea of the vertex with quadratics and how it doesn't really apply otherwise. So I do not want you to think that the peak is always going to be halfway in between these, because that is not true. It's very important that you realize that. So let me mention that again just to remind you. Note, if it is not a quadratic, the peaks or valleys do not have to be halfway between intercepts. That's only true for parabolas. Now you might wonder, is there a way to actually find those points? Find the peaks and the valleys where their locations are? The answer is yes, that's a part of what calculus is. So calculus allows us to find, for lack of a better word, vertices for random functions. That wasn't the point, but it's just it's a nice collateral benefit that we have from trying to solve the problem that calculus was meant to solve. So we have that, and one thing I wanted to do, now you could find the zeros of a function. I showed you how to solve equations on your calculator before. So you could find the zeros of a function by actually just telling it to solve that equation. But there is another function that I want to show you guys. There's actually a zeros function. Oh, and by the way, okay, maybe I'll say it. By the way, the zeros, I mean, this is something we mentioned before, but again, I want to hammer it home. We did this when we spoke about inequality way back in like the second lecture or something. The zeros help us solve inequalities also. Even on the test today, you have to solve some inequalities. So if someone were to ask the question, for example, if you had to solve this is greater than 0, what would the solution be? Well, if you could manage to graph this and find the zeros, you could just test points. You'll notice that it is greater than 0 in between -3 and 1. And it is greater than 0 when it's larger than 3. Right? So that would be the point. Now, just as how when we looked at solving inequalities, we said pretend it's an equation, solve for the zeros, and then you test points. We literally just did exactly that. It's just that now, in addition to that, I want you to be able to imagine a graph on top of that. So if you had to solve an inequality, and if someone asks you, where is this less than 0? You know it's from -infinity to the -3, and union -1 to 3. So the quick way to solve the inequalities is just plug that equation into your calculator, tell it to find the zeros, then test the points, and then it'll tell you where it's greater than or less than 0. Which I hope you actually used your calculator for that. One thing I've noticed in the past, for some odd reason, is that in the calculator section, I'll see students doing a lot of stuff by hand. I'm like, if you're allowed to use a calculator, why would you do it by hand? Like even if I'm allowed a calculator and someone told me to solve this, I'm not going to factor that by hand. I have a calculator, I'm just going to put it in the calculator. Every now and then I see a student doing a test and they're like, oh, I got stuck here, I don't know how to solve it. The TI-89 could solve, just plug it in. Get the answer. I don't know. I just want to show you how to find zeros on this. Not terribly important, but it might be a shortcut for you. Like I said, you could just find zeros by telling it to solve an equation, which we already showed you. First thing, turn your calculator on. That's where we were last time. Right, so that was the solve command. So if you wanted to find the zeros of something, let's say we want to find the zeros of that guy we had before. You had the option of going to algebra. You can tell it to solve, right? This is the old way. I'm just reminding you of the old way. X cubed plus x squared. I think it was -9. minus 9x minus 9 equals 0, comma, x. See, you could find the zeros there. So we found those already, 3 minus 1 and minus 3. The other option is what I want to show you here. There's actually a zeros command. So you'll notice here, if you go down to level 4, there's a zeros command. So when you actually put that command in, it'll actually solve this equation in the background, but it's pretty much the same. So the syntax for that is, once you enter the zeros command, you can type the thing in, x cubed plus x squared minus 9x minus 9. I believe you need to comment this here. So it tells you, find the zeros of this function in terms of the x values. And see, there it gives you the same guys, minus 3, minus 1, and 3. So it's just an alternative way. So that guy is not terribly necessary. You could still use the solve command as we've been doing in the past, but the zeros command is another option. One command that I would like, which is not going to be very useful for us, but it might be useful in other classes that you take, is you go to F2, where are you? Maybe it's not enough to. Because I wanted to be able to find complex solutions. Maybe it's under complex then. Complex. Okay, yeah. So we're not dealing with complex numbers, but if you're ever in a situation where you have to deal with complex numbers, you can go to the complex part of the menu and open this up, and you can have complex zeros, complex factor, complex solve. So for example, let's say I wanted to find the complex zeros of this function, x squared plus 1, or x, right? Now remember, for us, if I ask you to solve, set this equal to 0 to solve for x, you would tell me no solution, right? Because you can't take the square root of a negative number. But if you're ever in a situation where complex numbers are allowed, the C0 function would tell you what the solutions are in complex numbers, minus I and plus I. So that's nice. So it's just a nice thing to know. You'll never have to use that in this class, but I thought I'd just tell you since we're here. That's all I wanted to try to calculate. Yeah, just another way to find zeros. Just another thing to recall from here. This is supposed to be recall. We also spoke about symmetry last time. This means property of being self-similar. We covered even symmetry and odd symmetry. So we can talk about even symmetry or even functions versus odd symmetry, odd functions. And these are in the sense that the even functions exhibit even symmetry. This means it's symmetric about the y-axis. So one of the x to the fourth minus x squared was an even function. Realize it looked like this. That means it was symmetric about the y-axis. And the thing that defined the even functions algebraically is f of minus x is equal to the original function. I do want to emphasize here that if you need to determine something is even, you need to use this equation. There's nothing that will hint to you in the equation itself that's going to tell you it's odd. And I believe on the last quiz I even did examples of this. I gave you an example of a function where it had all odd powers, but it was an even function. So don't think that how the function itself looks is going to hint to you whether it's odd or even. Odd or even means it satisfies this equation. It's the only way you can know. There's no other way to know. If you have to determine if a function is even or odd, you need to check this equation. If this equation is true, it's even. If it's not true, it's not even. There's no other way to know. Okay. Similarly, we have odd functions. So these are guys that were symmetric about the origin, so something like that is an example. So it's kind of like you can, around the origin, rotate by 180 degrees to get the other one. Or you can think of taking the right side, flip it into y, and then flipping that into x, and you get the other side. And again, the only way to know something is odd is if when you replace all the x's with negative x. Remember what this means. F of minus x doesn't mean you put a negative outside. It means erase in x, open parentheses, and put minus x in, and then simplify. If you get the negative of the original function, that means it's odd. This is the only way to know if something is odd, other than seeing the picture itself. And even the picture is not good enough usually, right? Because you don't know how accurate this is drawn, right? If you have the formula, the only way to check if it's odd is to use this equation. Nothing in the function itself is going to hint to you that it is odd. It must satisfy this equation. There's no other way to know if something is odd. So don't just be, oh, they're odd powers, just x cubed everywhere. Doesn't matter. Another thing that I want you to recall, and this was in a previous section, but it connects back to this, is for quadratics. So they might display what we call the axis of symmetry. I believe that was also in the test today. So remember, when you're drawing quadratic, it will either have this shape, or it's going to have that shape. Right? The axis of symmetry just refers to the line about which it's self-similar. So the axis of symmetry is going to be that line that cuts like that, or cuts it exactly in half, where one side is a mirror image of the other. It's called the axis of symmetry. Could you find the equation of that line? Come again? No, the equation of the axis of symmetry. X equals negative b over 2a. Right? So it's an x line, it's a vertical line, so it must be x equals something. So if you know the formula for this is ax squared plus bx plus c, you're asked to find the axis of symmetry. It's literally the vertex formula gives the equation for the axis of symmetry. And it does that in either case. It's also true over here. Because the axis of symmetry will pass through the vertex. thing we want to talk about. So that kind of gets us up to speed to where we were last week, but I want to make sure that certain nuances are understood. The next thing I want to talk about in this section is the idea of a rational function. It's important that you remember what these guys are because we will be using them a lot in the coming sections. So what does it mean for a function to be rational? It's not crazy or no, that's not what it means. Rational, the word comes from, the root word is ratio. So it's talking about you're taking a ratio of two functions, but something is called a rational function when it's a particular kind of ratio. A rational function is one of the form y equals p of x over q of x. So it's two functions being divided in a ratio. Of course, your q cannot be 0 for that to be true. Where, here's what makes it a rational function. P and q are polynomials. So rational functions is when we divide one polynomial by another. So example, y equals x squared minus 1 over x plus 1 is a rational function. Y equals 2 over x squared plus 7. Y equals 14x to the 7 plus 3x squared minus 4 over 2 plus x minus 12x cubed. These are all rational functions. They are defined for all real numbers except the ones that make the denominator 0. So this one, for example, is defined everywhere. So these are rational functions. Now we're going to talk about their behavior a lot more in the coming sections. But for now, I want you to analyze these in terms of zeros as well, just as we were doing the other function. Analyze in terms of zeros. So let's look at two examples. Let's start with this one. Y equals x over x squared minus 1. How do you find its zeros of this function?
You do x squared minus 1.
How do you find the zeros of any function? What are the zeros? You set the whole function equal to 0. It's always how you find the zeros of a function. Okay. So if you do that, of course this would have to mean your x equals 0. Now, finding where the denominator is 0 is important for another reason, because that's important for the domain. So you might want to also find the domain. So you know if the denominator equals 0, this means your x would equal to plus or minus 1. So these guys are not in the domain. Right. So the function is not defined here. Now, I want you to realize what would happen in this case. The fact that your x cannot be plus or minus 1, how would that look on the graph? So let's look at the graph of this guy. Let's put in the xy. So if you're graphing a rational function, the points that make your denominator 0 are points you cannot touch because you can't divide by 0. And so in this case, it would be plus or minus 1. How that looks on your graph is something called an asymptote. And we'll talk about these in the future as well. In this case, there's a vertical asymptote. So this is not a part of the graph. It's just an invisible line, a barrier that we know we cannot cross. We cannot touch this barrier. So this is called a vertical asymptote because it's vertical. We'll discuss more about this later, after we cover the topic called limits. So it's called a vertical asymptote. So here, this one is at -1, this one is at +1. So we know these are values that we cannot touch. However, we also know that we have a 0 here, which, just like last time, we can plot. There's only 1 to speak of. But again, we would go through and we would test the intervals here. Okay. So we would test the intervals between the zeros, but now we also have to test around these asymptotes. Okay. So I'll plug in a random number over here, like a -2. Plug in a random number here, like a -1/2. Plug in a random number here, like a +1/2. Plug in a random number here, like a +2. And we are going to test in the original function. Or you can even test in the factored form if you want. X -1, x +1. So now, if I plug in a -2, I have a negative over, plug in a -2 here, that would be a negative. Plug in a -2 here, that's also a negative. So I'd end up having a negative divided by a positive. So that means it should be negative. If I plug in a -1/2, then that's a negative on top. -1/2 down here, there's a negative right here. And -1/2 here, that would actually be a positive over. So that one is here. If I plug in a +1/2, the top would be positive over, this would be negative, and this would be positive. That's negative, so I know the graph is down here. If I plug in a +2, the top would be positive, the denominator would be positive, and the x + 1 would be positive. That means positive graph is right here. Now here's where these guys kind of behave weird. They don't behave like polynomials. Then part of why I want to just do some naive sketches with you here is for you to realize how these guys would behave differently. But again, we'll talk about asymptotes and all these things in chapter 2. But for now, I just want your brains to start getting used to the idea of how these guys behave. The important thing is you cannot touch these red barriers. You cannot cross them, which means you are confined, right? So a guy who's up here is stuck up here, right? However, so I know the graph should be up here, but I also know it should eventually touch that point, okay? So, which means it should be looking something like that. But you see, he can't just go off and do what he wants. He's stuck inside this barrier, but he needs to constantly be going up. So what he does is he approaches this barrier, but he never actually touches it. That's why it's called an asymptote. It's something we approach as we go up to infinity, either horizontally or vertically. Okay. This guy is in the same deal. He has to stay stuck down here, except he knows he's supposed to touch there. So he would look like this. And again, he's always confined down there because he can't actually pass that barrier. So the middle of your graph will actually look like that. Now you have a guy who's always stuck underneath here. We know he will never touch the x-axis. He'll never touch the x-axis because there are no zeros over here. So what that means is we know he can't be moving up, right? So he's down here, but he shouldn't be moving up. He should definitely be moving down. So he has to be here, right? So now he's definitely down here and he's moving up. Now the thing is he can't actually cross the x-axis because we would have a 0. So he also has to treat the x-axis as a barrier. Because once he passes it, it creates a 0, which we know should be there. For a very similar reason, this guy would be stuck up here the whole time. He can't touch the x-axis because there's no zeros. We only touch the x-axis in one position. At the same time, he can touch this red barrier, but he has to be stuck up here. So that means he has to be increasing that way and decreasing this way. So that's what that picture would look like. And it would be a nice exercise to actually graph this on your TI-89 and look at what it looks like. But that's what that picture would look like. If we look at the second example. This is also a rational function. Now, here's an important thing. I'm going to try to simplify, but don't cancel. Right? It's very important that we're always aware of where our denominator is, what it's doing, because we don't want to divide by 0. So, does the top actually factor?
Yeah. 8 minus 4x.
Okay. So you see here what's happening is you would feel like we can cancel here. But what I want you to note is, remember, I want you to remember that part being right. Remember simplifying does not fix the domain. So the fact that you're canceling that x minus 3 in the bottom doesn't make x equals 3 okay. X equals 3 needs to still be avoided. We still need to avoid x equals 3. And again, in chapter 2, we're going to actually look at this in a very different way as well. But the point is here, what I want you to realize with this particular function, if we are not at x equals 3, then we could cancel to get y is equal to x minus 4, but we make sure that we still know it cannot be 3. And so essentially, our graph is going to look like this guy. Except that x equals 3. So it turns out this one is actually not half as bad to graph as that one. He will essentially look like the x minus 4 part, except you still can't plug in 3. What does the graph of x minus 4 look like? Huh? It's a straight line. How does it look? Like this? Okay, so it's going up, Does it cross through here?
No, -4.
-4 is the y-intercept, should be crossing there. So it crosses through here at -4. Right? It also crosses through here at 4. Right? Which means that our 3 is somewhere before there. I should probably draw on a 12-hour scale. And how you deal with this is at the 3, you put in a hole. Right? So at 3 it's still not working, but at all other points it's just behaving like this line. And that's something we'll analyze in a different light later on. But you can't have rational functions where nothing cancels, and so you have to avoid all these, you have to avoid an entire line of points. Sometimes things will cancel, you still have to know what the denominator is doing. You should realize that you simplifying doesn't fix the domain, and that will create holes. And we look at different ways to look at these guys. What else do you want to do? Now, at this point, I want to remind you about function transformations. I know some of you are probably sick of hearing of these, but I want to make sure you know them. It's basically us figuring out how certain algebraic changes to a graph will affect the geometric properties of a graph. So let's just list these. Given f of x. You guys can even tell me how to list these, how to do these. So tell me in words what these things do. So I could do f of minus x versus minus f of x. What does this do? If I replace all x's with negatives, what does it do?
Changes.
Change how? Be specific.
Horizontal movement.
It does what?
A horizontal movement. Like
No.
left to right.
This is a reflection. This reflects in y-axis. So maybe you guys don't remember that very much. So if I had a function that looks like this, and that's my f of x, then my f of minus x is going to look like this. It flips it in the y-axis. This guy reflects in x-axis. It flips it upside down. So again, if my function looks like this, then minus f of x is going to look like that. Flips it upside down. So these guys are called reflections. Now you also do have shifts. So if you have f of x and you add a constant, or f of x, you subtract a constant, this shifts up c units. This shifts down c units. I'm assuming c is a positive number here. So that's called a vertical shift. So if you have a function and I add a number to it, it will shift the entire graph up by as many units I just added. So I can look at f of x here. Let's say it looks like y equals x squared. Then f of x plus c is going to look like it's going to move up by c units. Whereas f of x minus c, it will move down by C units. So these guys are shifts, these are vertical shifts. So in other words, if we know what y equals x squared looks like, and I ask you graph y equals x squared plus 4, that should take you 0 time to figure out what that graph looks like. Just so, oh, it moves up by 4. A lot of times I see students, they need to plot a graph in order to solve a problem, and they're here plotting points. Once you pass pre-calc, you shouldn't be plotting points to draw a graph. Everything is now is a transformation. You know the basic pictures for several basic graphs, and everything to you now is just you shifting them around. You shouldn't have to plot points to figure out a graph. It's just a waste of time. You can do this inside, so you can have x plus c and f of x minus c. And these are also shifts, but these happen horizontally. You should also remember these guys kind of happen in an unexpected way. Sure, a positive you think would move up, negative moves down. You might expect adding a positive to the x should shift it to the right, but it's the opposite. This shifts left. The reason is the input value has to compensate in a different way than the output value for the change. This one shifts right. So these are also shifts. These are the horizontal shifts. So if you have y equals f of x, let's use some quadratic again. Then your y equals f of x minus c. We'll shift it to the right. As you can notice now when you plug in x equals c, it should give you 0. Again, consider c is positive, c is positive. Versus if I have y equals f of x plus c, that actually shifts to right by c units. So you can have reflections, you can have shifts, either vertical or horizontal. The next kind of thing you can have is stretching. So you can stretch things horizontally or vertically. So we can have f of x, and we can multiply it by a number. And this is a vertical stretch by c units. Here, assuming c is bigger than 1. And if you have 1 over c, f of x, vertical shrink by c units. So these are the stretchings and shrinkings. And so, an example here, say your y is equal to f of x. And let's say it looks like this. And your y equals c f of x, where your c is something that's larger than 1. We'll stretch it out. Horizontally, it'll cover the same distance. So if this is a and b, it will stay with a and b. But let's say this is at a 1, this will now be at a c. It will actually multiply the previous vertical height. Whereas y is equal to 1 over c f of x. We'll actually shrink it. So again, it's the same distance AB, but it'll make it squished. The height now will be 1 over C. So this is vertical stretching. You can also have horizontal stretching and shrinking. This is when you do something to the x values, so you can multiply all x values by a number bigger than 1, or you can divide all x values by a number bigger than 1. So this again, it kind of works in the opposite way you would think. This is actually a shrink. Shrinks horizontally. By a factor of C. This one stretches horizontally. So then let's say I had my y equals f of x. So equals to like that again. Let's make this 1 now. All that A, all that B. Then if I do y equals f of constant times x, like f of 2x, that will actually so leave 1 over C. Push it a little bit more, and if I have y equals f of 1 over c x, I'll actually stretch it out by c units. So the a, that will still be those are all the transformations you need to know. It's also important to know that you can actually combine them. Transformations can be combined. So given f of x, we could find something like a f of bx plus c, or something like that, right? Doing multiple of these transformations all at once. And so to deal with these, apply the previous transformation rules. Pretty much in the order of PEMDAS, believe it or not, that will actually work. So for example, let's say you had to look at this function, y equals minus 2, x minus 1 squared plus 4. So if you wanted to graph that, you pretty much start with your generic guy, just some variable that nothing's being done to it. And according to PEMDAS, the first thing you would do is square. Right? That's the first thing you do. If you see an expression like this, squaring is the first thing. The first thing you do is actually shift the x squared is the generic one, and the first thing you would do is actually do the shift, because that's in the parentheses. So you start off with the x squared graph, then you would actually just shift that 1 unit to the right. Next thing you do is you'd multiply that by the negative 2. Y equals minus 2, x minus 1. So you'd multiply by minus 2. That will now turn this graph upside down. I would also apply a stretch at the same time. And then the third thing you would do is apply the plus 4. And so your graph is going to move from here to this. Now this is a quadratic. We know how to graph quadratic. You plot the intercepts and all that stuff, but I just want to show you with an easy example how you plot using transformation. You start by something, and then you just start shifting and stretching based on what the operation is doing. You pretty much do them in order of PEMDAS. You apply multiplication, then the addition. So it's multiplying by a negative number, so we flip it upside down, stretch it by 2, and then shift up by 4. So you kind of do things in a certain order. And PEMDAS defines the order. Yeah, and in the handouts for this section, I give you even links to other articles for further reading. I mean, that's all the stuff we need to know, but sometimes it's nice to study around it to get a better understanding of everything. But yeah, that finishes 1.6. .7 is literally about one thing. It's about a circle. So I want you guys to remember that. The main thing there is to know how to complete the square, to figure out something in the circle. So we look at that. I believe I put a bonus problem like that where I said, here's some random function, it's a circle, tell me what its center and radius is. That's a very typical question. So again, something you should remember from geometry, but let's just go over it. A circle. A circle is a set of all points equidistant from some fixed point. So you can have a fixed point here. And now you can choose a distance. Let's say there's some distance here. this is your fixed point. And there is some distance, and you pretty much want to find all points that are that distance away. So here's one point that's that distance away, and you might say, oh, what if I measure that distance over here? Same distance, right, same d. Oh, well, there's a point there, and pretty much you're trying to plot all the points that's that same distance away. Eventually, plotting all such points will create a curve called a circle. So from this point, the distance to all these points on the outer edge, they're all the same distance away from this fixed point. And this blue line, this blue curve, is what's called a circle. So by definition, a circle is just a curve that describes all the points that are a fixed distance away from some point. So now, our fixed point is called the center of the circle. And the fixed distance is called the radius of the circle. Now, we often want to know, is there an equation that relates all these points that create that figure? And the answer is yes. So now we can talk about the equation of a circle. And to do this, we just use the distance formula, which is just an application of Pythagoras' theorem. So here is your center. Here is a random point on the circle. Let's call it the coordinate x comma y. And let's call the center having coordinate traditionally h comma k. And so now we actually want to measure the distance between these, d. By the distance formula. D will be equal to, or let me just derive the formula as you'd see it. Let's call it r for radius. This is r, that's the distance. By the distance formula, that distance r is going to be equal to the square root of the difference in x coordinate squared plus the difference in y coordinate squared. So I can take x2 minus x1 and take y2 minus y1, and that will give me that, right? That's a formula to get the r. And customarily, we would square both sides. And we would get x minus h squared plus y minus k squared equals r squared. And this is the guy we're after. So this gives us the equation of a circle. Let's actually just write that down. Equation of a circle. With radius r and center h comma k is given by this expression, x minus h squared plus y minus k squared equals r squared. I want you to note h, k, r are constants. X, y are variables giving coordinates the circle. So that is the equation of the circle. So it has center h comma k, radius r. This is going to be its formula. So that's just, if you probably had this memorized already, but if you haven't had it memorized, you need to memorize it now. That's what the equation of the circle looks like, right? And you need to know what is h, what is k, what is r. The center is h comma k, and the r is the radius. So here's the issue with us. It's not an issue, but the common type of problem is it's usually not going to be given to you in this form. It's you have to put it in that form to be able to answer the questions they'll ask you. So what you want to note is that we can expand this equation to write it in the form, say, x squared plus y squared plus ax plus by c equals 0. So now this is a special case of a larger group of functions called conic sections, but a conic section that looks like that is what we call a circle. Your a, b, and c are constants, and your x and y have coefficients +1 respectively. Whenever you have that happening, you have a circle on your hands. And sometimes you will be given the equation of a circle in this form, and you need to figure out its center and radius, right? Trick, and never the trick, is to use completing the square. So the reason why I reviewed completing the square when dealing with quadratics, even though no one ever uses completing the square when dealing with quadratics, is because I wanted you to remember how to do it for this section. You will notice that this is a complete square, and so is that. So if these are not as is written, you need to create them, right? So you need to know how to complete the square in order to create this form from that form. So we already reviewed completing the square, so at this point we're just going to do some examples and be on our way. So we're going to go through 4 examples. And yeah, with this kind of problem, very usually this is exactly the kind of question they ask you. They give you something that's written out like this, and they say, find the center of radius. So this is find the center and radius of the. So we're going to go through 4 examples here. Yeah, so on a final, you'll definitely get something like C or D. Like, they're never going to ask you this. I just want you to get used to the formula. But a problem would sound something like, this equation represents a circle. Identify its center and radius. Pretty much verbatim is what it's going to sound like. Right? And that'll be like one of the problems in the final. It's usually in the non-calculator section, so you do have to know you're completing the square root solving, so that's why I went over it. A. What's the center and radius of this guy? H comma K equals 1, -2. What's the radius? 2. This here is the center. This here is the radius. Now you obviously know what you're doing, but I want to emphasize to everyone else. Do we see why this is a -2, for example?
Because it's deriving to the right.
Right. What you need to remember is the general formula that I had written down here that I erased has a minus sign in it. So once you want to start identifying people, you need to put it in a certain form. So here we had x minus 1 squared plus y plus 2 squared equals 4. You need to be able to identify the numbers, you need to write it exactly as that in that form. So you'll notice in that form there was a minus sign, whereas here we have a plus sign. That is a problem, right? The first thing you realize is that we need to rewrite this so that there's a minus sign. But how can I rewrite a plus 2 if you're forcing me to use a minus sign? Well, you do minus a -2. Right? That will make it a plus 2. Okay? So, and on the other side of the formula, we have something squared. So having a 4 there is not very good for us. We need to be able to write that as something squared. So pretty much we take the square root of this and then write it as the square root of this squared. The square root of 4 is 2. 2 squared. So here we can now readily identify who's the h because he's the guy who's after the minus sign. The k is the guy who's after the minus sign here, and the r is the base of a square. So it's not you would just pick like 1, 2, and 4 or something like that. You need to make sure the signs are matching up. So if there's a positive sign here, it's actually you take the negative for that coordinate. You change the sign. So you see a -1, it's a +1 is in that coordinate. See a +2 is a -2 is in that coordinate. Because you have to kind of match it up to that form that we derived earlier.
But with the 1, why do you put it for positive if the form is negative?
I didn't put anything positive. It's still minus. Huh? Yes, for the same reason. We have x minus h squared plus y minus k squared equals r squared. So according to this, and I know that the center is h comma k, which means whoever is behind a minus sign, I'm putting that here. The 1 is behind a minus sign. Put it there. Right? Now in this case, this guy wasn't, and here, whoever's behind this minus sign is the k. But here there was no minus sign, so I just rewrote it. And that's the guy behind the minus sign. It's minus k. This has to be k. That's going to put in that center. So essentially, it works out to you changing the signs before you put them in the coordinate. You have to remember to do that, because there's a negative in the formula. What about B? What's this one? So we had x squared plus y squared equals 3. What do you think? 0, 0, square root of 3, because we are rewriting it in the form. So x, I can think of it as x minus 0. The y, I can think of it as y minus 0. And the 3, I can think of it as radical 3 squared. So that's what I see. So here, that's my h. Here, that's my k. And this guy is my r. And so here I'd be able to say the center is 0, 0, and the radius is radical 3. Let's do the more challenging ones. Okay, so on a test or a quiz or a final, it's one of these two types that you'll see. So it'll be much more familiar to this one. I'll write that one over here. Okay, so how do you deal with this one? So as before, again, we're rewriting it in a certain form so that we can pick out the right numbers. So how do we go about rewriting this in a certain form? Okay, combine like terms. So first, what we would do is group x's, y's, and constants. Right? And constants we can put on the right side. So the first thing I'm going to do is just a rearrangement, kind of write things out, put them in a nice order that I'm going to start before I do anything. So I'm not really doing any calculations right now, I'm just rearranging things. So I'm going to put the x's beside each other, put the y's beside each other, and constants on the other side. So that would be my first step to rearrange things. So step one is to rearrange. So what's the second thing? Oh, well, you mentioned it. The second thing is now to complete the square. For x and y individually. Now, remember how we complete the square. So for x minus 2x. Remember, you add and subtract something squared. And so for the y, 4y, we're going to add, subtract something squared. Okay, so now what is the thing that we add and subtract? What is being squared here?
Half of 2.
It's half of the coefficient of x. So minus 1 goes in here and minus 1 goes in there. So this half of positive 4 is positive 2. And what happens now is the first three terms become a complete square, right? So it's going to be x, that guy on the inside, all squared. X minus 1, all squared. This guy that we created, he just stays, so that's minus 1. Plus, now this guy, the first three terms here will become all squared, become a complete square. It's the y plus the guy on the inside, which is a plus 2, all squared. Here I have a minus 2 squared left over, just leave that. So that's the first thing. So that is completing the square. Okay, now the third step, after that point is just to rearrange again. And write in the general form. So in our general form there shouldn't be numbers over here, so I'm going to take these numbers and move them over there. So I'm going to add 1 to both sides, I'm going to add 4 to both sides, and ultimately I will end up with x minus 1 squared plus y plus 2 squared equals 4. Now of course I'm thinking of this 4 as 2 squared. And so ultimately now put it up here. I can talk about the center and the radius of this circle. So the center is going to be what? 1, -2. And the radius is 2. Right? Just like the first one. So that's going to be your answer. So you're given it in a very inconvenient form. The trick is group x's and y's together, move the constant over the other side, complete the square, and rearrange. And then you'll have it in a very nice form to be able to talk about the center. What about this one? Well, we do the same thing. Step 1. Group the x's and y's. Move the other guy to the other side. Step 2, we need to complete the square. Now, completing the square, remember, works differently when the coefficient is not 1. Okay? When the coefficient is not 1, what you want to do is you want to factor it out. So what happened here, coefficients were not 1, so we factor them out. Now, what you want to do is complete the square inside the parentheses. So now I'm going to do, that's x squared minus 3x squared minus 5y. And as before, I'm going to add and subtract something squared. Add and subtract something squared. Now, what is the thing that I'm squaring? What goes inside here? Half of minus 3. So minus 3 over 2. And I put that in both places. Similarly here, minus 5 over 2. Just double the denominator of whatever's in front of the linear term. So that would mean the first 3 terms will be a complete square. It's going to be x with the guy inside the parentheses, all squared. Then you're going to have this guy left over, so that's going to be a minus 9 over 4. That's this guy here that's left over. So these first 3 are the complete square, and then that guy's left over. He's inside the parentheses, which is very important because this 2 is going to have to multiply out and change him. Okay, moving on. So the first 3 terms, when you do this maneuver, will become the complete square. It's going to be y plus the guy on the inside, which is minus 5 over 2, all squared, minus this guy, which is going to be 25 over 4. It's just the leftover piece. Okay, so now we're in the last step. We have to rearrange now. So we have to multiply out, rewrite in the standard form. I'm going to start to multiply out these 2's. So now we're in the third part of the process. So we have 2 times x minus 3 over 2 squared minus 9 over 2 plus 2 times y minus 5 over 2 squared minus 25 over 2 equals minus 9. So first, leave these guys. and I'm going to bring all these guys to the other side. So I'm going to have minus 9 plus 9 over 2 plus 25 over 2. So that side is actually going to be what? That is minus 9 over 2 plus 25 over 2 gives what? Is that 16 over 2? Alright, so that's 4.
Is that 18?
What? Is it 18?
No way.
Because minus 9 is 18 over 2, right? So if minus 18 over 2 plus 9 over 2, we get minus 9 over 2. And you take 25 minus 9. That's 16, right? Okay. And that's all over 2, so you get 4. And so now what you want to do is you want to divide by 2. So this gives you...
Wait, isn't it 8? 16 divided by 2?
Well, I was correct, just not where I thought before. So now I have x minus 3 over 2 squared plus y minus 5 over 2 squared and 8 over 2, because I just divide by these 2's here. So what is the center? Was the radius. Any questions on that? Yeah.
How come over there is 25 over by 4 and we changed to 25 over by 2?
Oh, I expanded. Don't forget there's a 2 out here. There was a 2 out here that I factored out from the beginning. That has to multiply out now. So the 2 times the 9 over 4 gives me a 9 over 2. And then add 2 times this and 2 times that, and 2 times the 25 over 4 gives me the 25 over 2. Other questions? We'll actually stop there for today. So next time we will do 1.8, finish that up, and then move on to chapter 2. Chapter 2 is where calculus starts to happen, so I'm very excited for that. You guys are probably tired of all this algebra. So by next
Because
class.
I don't remember this.
Oh, well now you remember. That's why I'm going over. I didn't want to skip it. Yeah, so we'll actually stop there. I have some blank copies of version B of the test there. If you want to go over that with that in the recitation session, you can do that.